So we'll do a quiz on shift registers. You don't have to write onto the quiz. So you are going to open up a GVM editor and type in there and send it to my email. I know you probably won't be able to debug it just in GVM, which is okay. As long as you have the main part of the script written or typed in there, I will give you partial or full credits. Depends on what you have in there. Right. Okay. And here's a demonstration video of it.
This is a serial in, parallel out.
So when you are typing it into your GVM, you should always think about the implementation.
The rising edge is going to send 1 bit of the
you'll be able to hear that when you play it on your end. So what's happening here is it's a shift register, serial in, parallel out, and we're not using any digital clock. It's a manual clock, which is the switch. Your finger push it up is the rising edge, and that's a clock. So that's how you can visualize it because it's super slow. So you have to debounce that switch. Use 2 switches. One switch provides data, which is switch 0 is a data, and switch 1 is clock. Okay. So for example, I'm trying to do a serial in, parallel out shift register, which is giving 1010 to it. Okay. So when I'm doing that operation on the board, I need to turn on switch 0 first, so it's giving a 1, right? Then I use a switch 1 as a rising edge to put it in, so it's going to be injected into the shift register. Then I turn off switch 0, give a 0, and then providing a rising edge. Just keep doing that for 4 bits, so eventually you're getting 1010 as the data input. So at the 4th rising edge, it finishes the 4-bit. It's very similar to the data transmission, for example, serial or UART. It's usually 8 bits, just 1 byte. It sends 8 bits. When it's ready, it turns on a flag and make that data ready, so all the other register can read it. It's very similar, but we are not turning on any flag. It's just 4 bits after the 4th rising edge. It should show the result on the LED. So it should show 1010 on the LED. Is that clear? After 4th. So it should count to 3. Okay. If you start the counter with 0, you know what I mean? So if you do like count equals 4, then do something, then you need 5 cycles because it starts from 0. Unless you initialize your counter as start with 1, right? So it's counting from 1, 2, 3, 4. So it's 4 cycles. If you don't do that, just put a default value when you declare it, it's going to be 0 by default. So you need to use 3 as a count max instead of 4. So when the counter equals 3, right, then you do something instead of 4 because it starts with 0. So it's going to be 0, 1, 2, 3, so 4 cycles. Okay. Let's come back here. Now let's play the video, even though you couldn't hear that really clear.
This is a serial in, parallel out shift register, and switch 0 is the data, and switch 1 is clock. So rising edge is going to send 1 bit of the data at switch 0 to the register, and after 4 cycles, it's going to output everything to the 4 LEDs. So I'm trying to output 1010 to the LEDs.
So the final result looks like this.
You can see.
Okay, just the 4 LEDs. Okay, 1010.
I'm getting 1010 as a result.
So I have 20 minutes for you guys to work on it.
We need to do the test bench.
No, yeah, test bench. So I have instructions on the quiz.
Oh.
So the test bench and the code, just type it in there. You don't have to debug it. Just type it into the GVM and send it to me by email. And by 5 p.m. today, you should have done
debug it after the class, or you can work on it after the lecture. Which of those you have time, or you can work on debugging your implementation to FPGA after class. It's very simple, it's super short, just a couple of lines. But yeah, it's reasonable.
I contact IT to try to let them fix all the Vivado in the computers. In the future, when we do the quiz, we don't have to, type it and then debug it afterwards, right? And hopefully the IT will fix the Vivado, so we don't have to do a typing in the class and debug and implement it after the class. Because not everyone has a laptop.
Why do you have debug for switch 1 but not switch 0?
Because it's a constant data. It's on, then it's on, right? Your finger's so slow, your finger's not moving like a flash. You turn it on, it takes a while for your fingers to move to switch 1, right? It's a state, it's holding there. And it's waiting for the rising edge. So if you don't have the rising edge from switch 1, it's not going to do anything to it. So even though it's bouncing back and forth for switch 0, it's not a problem. Cool. Okay, VGA is a very fun part. It also lays a groundwork for the course project, which is the game, IPGA game we are going to program on the board. So you need the communication from your IPGA to the monitor. I have all the cables. I'm going to give you one of you, each of you a cable. So the only less exciting part of it is VGA is just too old kind of technology. Nobody's still using that. If you look at the laptops, the new laptops, they all abandoned that VGA port. So probably next year when I have to teach this again, I'm going to do a like VGA to HDMI converter or something. But I think it's good to understand what's really going on for this 20-year-old technology. A lot of really interesting things to know. If you look at the pin out of the VGA port, okay, it is pin 1 to pin 15, okay, and pin 1 is the red video. We have RGB, red, green, and blue. So it's number 1, 2, 3. And you have all the other things like the RGB's ground pins. This is providing a reference, and overall ground, the monitor ID. I don't know what that is, since I didn't use it. You don't even have it programmed in the controller. And there are a couple of other signal lines that I'm going to talk about. For example, the sync, horizontal sync and vertical sync that you have to program in your VGA controller on IPGA. So one thing you have to think about, like red, green, and blue, these 3 pins, it's just 1 bit, right? How that works? Is that possible? You're trying to transmit the video signal and it's just 1 digital line in there. How that works? What are the possibilities? I let you guys just tell me, based on your background, what you have learned. Okay, just 1 pin for 1 color video. Serial could be possible, right? But it's not. But I mean, it's good that we know serial is a possibility. We just program this shift register, right? Can serial in parallel out, right? What else? What else? What else you can think about? That's also serial, right? What's the other possibilities you can think of? Just 1 line to transmit a video data for 1 pixel. It's just the so the pixel data is just the intensity of the color usually, right? But you do need if it's digital data, you do need a few bits to represent that intensity. If it's just 1, 0, what is the color? 1, 0, black and white, right? So you won't be able to represent all the gradients of the color from 0 to 1. So I was looking at the details. This is actually a analog pin. It's an analog voltage. But how do you output analog voltage using digital pins? It's IPGA. And IPGA is all about outputting digital signals. How do you get the analog voltage to reach there? You know. Yeah, that's right. That's right. Yeah, if you look at it, so the first time I saw that, I was thinking they may have a DAC somewhere, but actually it's not. They don't have a DAC. But the superposition is a resistor string-based DAC. If you are going to take digital next year, so you'll learn the R2R DACs. So the DACs are using superposition to convert digital signal to analog. If you look at the diagram, I just updated the web page over here. You can see the red. So you have 4 bits for red, right? I have different resistors. It's actually an R2R. Not R2R. It's a ladder, resistor ladder. Should we have a quiz on superposition? You will have a few quiz on superposition in digital next year. So it's good to understand what's going on for superposition. So basically, if you have a 1 here, right, you ground all the other sources, and then you calculate the voltage contribution from that source independently. So you are actually looking at individual contributions to the same node. So eventually they are adding together, adding up or superimposed to each other to form an analog voltage. So you should know that the VGA ports, unlikely they are going to interview you about VGAs, because if they have to put some like video transmission question on the interview, it's going to be HDMI. But it's good to know this, right? So it's an analog voltage for each color, but the output from the controller is still digital. Okay, so now the task for computer engineers is to program that logic for the controller and send specific digital signals to the port of the VGA controller, then display single individual pixels on the monitor. So we have to follow a standard. You know, how many pixels vertically and horizontally for the VGA controller, you have to follow a standard. So there's a website listed all the standards of the frame, the number of pixels for different protocols. This is the most common one. It's really old, I think 30 years old one. That's why teaching in this field is sometimes getting overwhelming because you have to learn new things every single year. You don't keep teaching VGA. Now it's still fine, right? Because I bought this laptop probably 5-6 years ago, still has a VGA. But now none of the laptops has a VGA port. So still okay to teach it this year. Next year, 2 years later, I'll be embarrassed if I keep teaching this. You know, guys will learn how HDMI works. 640 pixels by 480 pixels. So it's 640 horizontally and 480 vertically. And it defines all the details on the website. And if you click it, you can see the specs in the table. So the screen refresh rate is 60 Hertz. It's a screen refresh rate. So when you look at the VGA, if I plug a VGA to the monitor, it's refreshing the monitor screen at 60 Hertz, which means it's about 60 frames per second. So I cannot resolve it because refreshing so fast. So 60 Hertz usually will give you a pretty smooth video display. So are you able to calculate so now you know how many pixels you have, right? You have this many pixels and being refreshed at 60 Hertz. So are you able to calculate what's the frequency for to update each pixel of the monitor? It just divided by this many number of pixels, right? 60 Hertz divided by this guy, right? 60 Hertz divided by the total number of pixels. So somewhere around like 25 megahertz, that's a pixel refresh frequency. So you are assigning each pixel to the monitor at 25 megahertz, like placing pixels to the monitor at 25 megahertz. Okay. And it has a certain timing diagram you have to follow. So when you program the Verilog, your Verilog for this VGA controller, you have to follow this diagram. So one period starts from here and ends here, because that's the starting of the back porch, and which is the starting of the back porch over here. The end of the sink and the starting of the back porch. CNC is repeating, right? So that's the back porch over here, and that's the back porch. So one period is basically from here to here. And this diagram can be confusing sometimes, and you're thinking, what's the x-axis over here? And why do we have a area that is not actually assigning pixels to the visible area of the monitor, but doing something else? So they are all for controlling purposes. But for this period of time, what's the purpose of it? So this region is a visible range of the monitor, so you are basically assigning pixels to it. Okay, but after that, you just basically stop after that clock. I mean, more details? Could you provide more details? It's very close. So it allows the pixels to dim. If you have the visible area and then immediately followed by another frame, they're just too close to each other. It's probably not totally discharging all the caps for the pixels. So give you some time over here to discharge all the colors over there. Okay. So what's the x-axis of this diagram? It's a really no-brainer question. Time, right? And these are the clocks, which does all the clocking Oh no, sorry, this is a sync. So if you zoom in from that frame, this could be very confusing. So if you see this sync signal, this pulse, and it makes this area longer to let you see the visible range, but it's basically just one period of this signal timing frame. So this the two low voltage zeros, zero signals, should be aligned with these two zero signals over here. It just zoomed in everything, lets you see the details of it. Okay, so what's going to happen is you have to run through all the timing, and every period has a definition of the standard of how many clock cycles you need to put in there. Okay, so if you look at these two tables, okay, so on the top it's a name of the period and the pixels. This could be confusing, but it's not basically pixels, it's the pixel cycles, it's actually clock cycles. So you need a 640 clocks, you can understand that way. 640 clocks. Okay, that's the time it takes to finish each period. You have a visible area, the front porch, the sync pulse. So let's take a look at timinggram. Where is the sync pulse? It's over here. So you need to put it down to 0 as a signal to show that the line, the horizontal line or the vertical column is done as like an end signal. So you just put it down to 0. So because this is being defined in the timing diagrams, you have to program it in your Verilog, have to make it happen. So you put it down to 0, and the table defines about how long you need to hold it there for 0 as a 0. So this is a vertical sync signal line. So we want to look at this vertical timing frame, and the sync pulse only takes 2 clocks. So that clock, what's the frequency of that clock? So I told you at the very beginning, the pixel assignment is at a certain frequency. We calculated from the frame, the screen refresh frequency, which is 60 hertz, right? And we know the number of pixels, which is 640 times 480. Okay, so we use 60 hertz divided by that number, and we're getting 25 megahertz. So that's the clock frequency for each pixel. Okay, so that's the basic clock timing for all these numbers here. So the sync pulse here requires 2 clocks. Requires 2 clocks to finish, and similar to these ones. So the back porch need a 33 clock cycles of 25 megahertz clock. So when I'm talking about this, when you are hearing what I'm talking, you can think about when you program Verilog, how would you like to code it up, based on what we have here. It will be a number, right? Whenever the clock, the counts reaches that number, then we do something. It's just a number. So you have always rising edge of the 25 megahertz clock. It's keep counting as a base, as a reference for standard signal. Then you start from there to, count to these specific numbers to do kind of task. All right. So the Verilog scripts are all provided for most of the demonstrations, and it's very easy to understand. It's totally following the timing diagram over here. Okay. We are looking at the timing diagrams. They are just the counts. Could you understand that? These are just the number of counts. Since you have always rising edge of the clock, which is 25 megahertz. So when you are doing this, it's just the counts, number of counts, because you can find out the number of counts over here for each period. So you are basically just counting to that number, then do something else. Use the else, like if it reaches something, then do something. Okay. So for the VGA controller, it's nothing but all the nested if statements. See if you are reaching that count. If are, for example, you are doing it here. If it's not reaching the count here, then you keep assigning pixels to the port. Okay. And same here. So if you finished the assignment of the visible pixels, but not here yet, so you don't do anything. If you reaches here, then put the sync signal down to 0. That's it. It's just based on counts. Until this count, you do something, right? That's it. Just follow the timing diagram. See? These are all the different counts. You count to here, you count to here, and you count to here to do different tasks, following the timing diagram. See, if it reaches here, set the sync signal to 0. So put it down to 0. That's it. And this is a diagram of the project we are going to work on for this tutorial. Okay, so the VGA controller is just a IP block we are going to design, just a module. Okay, so this module does all the counts and it outputs an address. The address is going to send the address to the ROM, and the ROM will store a image file in there and return that pixel data back to the VGA controller. Because you have to use the VGA controller's interface to send a signal to the RGB ports, of the IPGA board. Because that's eventually the IPGA board has a VGA port. So that's IPGA's VGA port, and it has a certain number of bits for each color. At here, but when it arrives at the VGA port of the IPGA, it becomes analog because of this. Because of this, you see all these digital bits of the color of the data is being superimposed to one node, and eventually becomes the analog voltage for the VGA port, for the physical VGA port. Okay, and you need a clock, and the clock we used for the tutorial is the IP core of the Vivado software, and so you can create the IP for the clock. It's creating a 25 megahertz, clock from the IP, and I think I probably has another task for you guys to make a clock frequency divider to generate a 25 megahertz clock by yourself. But I think the first couple tasks just using IP block. Now let's take a look at the pixel assignment over here. Whenever it reaches the count reaches the visible region, so you are supposed to send the pixel data to the VGA port, and these are the data for the ports. See? This is the pixel data 220, that's 3 bits for the red color, and 345, that's 3 bits for the green color, and 2 bits for the blue color. So totally you have 8 bits for the for the VGA port. For each pixel, it's 8 bits. It's not the best resolution. And for this demonstration, I assigned all zeros to red, and all zeros to green, all zeros to blue. All right. If they are all zeros, what you are expecting for the VGA? Should be white or black. it was white, but I was thinking like, why is not black? You have to look at the table. I think I have a link provided on the tutorial so you can find out the code for each color. I think it's here, the RGB chart, right? Oh, so 00 should be black. 01 should be white, right? It's 255 is the 8-bit. It's 8-bit for each channel, but actually we are not using 8 bits. Okay, so the color won't be as good as the 8-bit color frame, but you won't be able to tell for the white color if it's all white. Your white is better than my white. Doesn't make sense. It's all white. But for this one, so this is a basis 3 picture, the board picture. You can see the board should be blue, right? It looks like something in between blue and green, because you only have 3 bits for R and G and 2 bits for B. So B is not being represented really well. I only have 2 bits, which is four different levels for B, which makes sense. So this will be a little picture being displayed onto your monitor as one of the demonstrations. And also you are going to assign solid colors to the monitor. So it's showing a solid color and also switching in between different colors, just solid colors like this. So this shows the transition from R and G and B at 1 Hertz, I think. So for the tasks, I have a second task. Here is a replace the clock generator IP for a self-made clock divider to provide 25 microhertz. You have to write up a clock divider or frequency divider to create a 25 megahertz clock. So the first one, the third one, or if you follow the examples in the tutorial, it's letting you use a clock divider. Let's see, like this one. It's an IP core. Okay, it's a super simple to generate by yourself. So that's why I added another task over there. Okay, that's for the tutorial. And on Thursday, we don't have a lecture in the classroom. You can work on the VGA tasks on your own, wherever you want. And in the lab, I'm going to be in the lab, 760 electronics lab, for a 2-week lab. It's a tools complement adder. So most of you have worked on this, either on the layout task in the digital electronics class, or in probably in the basic fundamental logic class, a little bit on IoT Spice or Electrical VLSI. But here is a different way to implement it. And compared to last year, I added a step 3 as week 2. So this week, you guys are going to work on step 1 and 2. Try not look at other people's references and just work on it by yourself. I'll give a short lecture on Thursday in the morning. I know at 11:15, and then you will be able to work on this the week 1's task. Hopefully, you can finish it. On that day, right? And next week will be a step 3 of the task. So what's happening is it's a calculator. So for step 1 and 2, you are giving the numbers through the switch, like 2 3-bit numbers, and you are doing addition and subtraction using your calculator design on the IPGA. So step 3 will be a serial in parallel out input. So I have to put all the data or the numbers in serial manner into the register and then trigger the calculator using a switch. Okay, so that's the plan for the lab this and next week. And tutorial is just a VGA. And today by 5 p.m. you should upload your quiz results to the website. And there's a homework 6 for today's the VGA tutorial due next Tuesday. And next Tuesday, we're going to start a new project, which is the UART. Very practical. The TX and RX are Arduinos. It's just everywhere. Important. All right. Any questions about the tasks this and next week? Okay. So you can start working on the VGA project, either here or anywhere else you want. These are the VGA cables.